hundreds of feet below the surface of Iceland, superheated water bubbles in natural reservoirs. This is not an isolated phenomenon. It is the daily life of a country that has transformed its unique geological position into an energy revolution that powers almost all of its infrastructure. Welcome to another video on the channel. Today we will explore how a small North Atlantic country manages to heat 90% of its homes, produce electricity in abundance, and grow tomatoes in the Arctic Circle. All this thanks to the heat that comes from the depths of the Earth. Let's discover not only what geothermal energy is, but how Iceland became a world leader in this technology, and why this may represent the energy future that our planet needs. While Iceland enjoys its energy abundance, the rest of the world faces growing challenges. Global energy consumption is constantly increasing. Projections indicate a growth of 50% by 2050, driven by the industrialization of emerging economies and population growth. At the same time, we face multiple interconnected crises: climate change intensified by the burning of fossil fuels, geopolitical instability affecting oil and natural gas supplies, and the urgent need for electrification of sectors such as transportation and industry. There are some effects that are already visible globally. Number 1, extreme weather events have disrupted power grids in various regions. 2, international conflicts have caused spikes in energy prices, directly affecting consumers and industries. Number 3, the demand for critical metals for renewable energy technologies is creating new environmental and economic pressures. Number 4, countries dependent on fossil fuel imports face growing vulnerabilities. Amid this complex scenario, geothermal energy offers a promising alternative: constant, independent of weather conditions, with a low carbon footprint and potentially available in various territories. The Icelandic experience, therefore, is not just a curious case of local adaptation. It is a model that can offer valuable lessons for the global energy transition. Geothermal energy is, in simple terms, the natural heat of the Earth. This heat is mainly generated by the radioactive decay of minerals in the planet's core and mantle, creating temperatures that can exceed 9,000 degrees Fahrenheit at the center. As this heat moves from the core to the Earth's crust, it heats groundwater, creating thermal reservoirs and, in some cases, surface manifestations such as geysers and hot springs. What makes geothermal energy particularly valuable is its constancy. Unlike the sun or wind, the heat of the Earth is available 24 hours a day, every day of the year. But why can Iceland harness this resource so well? The answer is literally in the geological DNA of the country. Iceland is located directly on the meeting of two tectonic plates. These plates are moving apart about 1 inch per year, creating a zone of great volcanic activity. The country is home to more than 200 volcanoes, 30 active volcanic systems, and about 600 hot springs. Additionally, the Earth's crust in this region is significantly thinner. In some places, it is only 6 to 9 miles thick, compared to the typical 19 to 31 miles in other continents. This means that the heat from the Earth's mantle is much closer to the surface. This unique combination has made Iceland a true natural laboratory for the development of geothermal energy. The proximity between population centers and geothermal resources has also facilitated the development of the necessary infrastructure, minimizing losses in energy transmission and distribution. The real turning point, however, came with the oil crises of the 1970s. With oil prices quadrupling virtually overnight, Iceland dramatically accelerated its investments in geothermal development. The country created institutions dedicated to geothermal research, established specialized training programs, and developed its own exploration and utilization techniques. This long-term commitment to geothermal energy has radically transformed the Icelandic economy in the following decades. What began as a necessity became a national competitive advantage, attracting energy-intensive industries such as aluminum smelters and data centers, which benefit from the low cost and reliability of Icelandic electricity. The process of capturing geothermal energy in Iceland follows different approaches depending on the end use. In many areas, water naturally heated to 176 to 194 degrees Fahrenheit is pumped directly from hot springs to an urban distribution system. This hot water circulates through a network of insulated pipes that extends for more than 2 miles, heating homes, businesses, and even melting snow from sidewalks and roads during winter. The system is so efficient that, when leaving homes, the water still maintains sufficient temperature to be used in public pools and geothermal spas, such as the famous Blue Lagoon. This cascading use maximizes the energy efficiency of the resource. Icelandic district geothermal heating systems are notable for their simplicity and durability. Hot water is pumped directly into radiators in homes without the need for individual heaters or complex heat exchangers. The underground pipes are carefully insulated and can last more than 50 years with minimal maintenance. In practice, this means that Icelanders rarely face heating problems, even during the harshest winters, when outside temperatures can drop to 5 degrees Fahrenheit. The contrast between the intense cold outside and the comfort of geothermally heated homes is one of the first things visitors notice upon arriving in the country. To generate electricity, Iceland drills much deeper wells, reaching 10,000 feet in some cases. At these points, the water reaches temperatures above 572 degrees Fahrenheit under high pressure. Iceland's energy transformation is expressed in impressive numbers. I'll list them below for you. Number 1, 90% of homes are heated with geothermal energy. Number 2, 30% of the country's electricity comes from geothermal sources. The rest comes mainly from hydroelectric. 3, 5 large geothermal plants produce 755 megawatts of installed capacity. 4, the cost of residential heating is approximately 1/3 of the cost in countries that depend on fossil fuels. And number 5, energy-related CO2 emissions per capita are 87% lower than the OECD country average. Before the large-scale implementation of geothermal energy in the 1970s, Iceland imported coal and oil for heating, spending about 8% of its GDP. Today, the country saves approximately $100 million annually thanks to its energy independence. This revolution has also transformed Iceland from one of the poorest countries in Europe into one of the nations with the highest GDP per capita in the world. Energy security has allowed the country to better withstand global economic crises and develop high-tech industries that depend on reliable and low-cost electricity. The impact goes beyond economic figures. Air quality in Icelandic cities has improved drastically after abandoning coal for heating. Reykjavik, which previously suffered from considerable pollution during the winter months, is now recognized as one of the capitals with the cleanest air in the world. Additionally, the energy transition has created a new economic sector of specialized knowledge. Iceland has become a global exporter of geothermal expertise, with Icelandic engineers and geologists working on geothermal projects on 6 continents. Geothermal energy in Iceland goes far beyond heating homes and generating electricity. The country has developed a cascade utilization system where heat is used repeatedly in different applications as its temperature decreases. In a country where average temperatures rarely exceed 59 degrees Fahrenheit in summer, Iceland manages to grow tomatoes, cucumbers, peppers, and even bananas in geothermally heated greenhouses. These greenhouses not only provide local production of fresh vegetables, reducing the need for imports, but also use advanced cultivation techniques. Many employ LED lighting to compensate for the few hours of sunlight during winter and hydroponic systems to optimize the use of water and nutrients. Moderately heated geothermal water is also used to maintain ideal temperatures in fish farming tanks, allowing the cultivation of species such as tilapia and barramundi that would normally not survive in the Icelandic climate. In addition, the silica and minerals present in geothermal waters form the basis of dermatological products that are exported globally. Researchers have discovered that certain microalgae that survive in the extreme conditions of geothermal lagoons produce compounds with exceptional anti-inflammatory and antioxidant properties. The experience of bathing in natural hot springs while observing the northern lights or the volcanic landscape has become emblematic of Icelandic tourism. Besides the famous Blue Lagoon, dozens of municipal pools in each small town and village provide community spaces where Icelanders gather daily, transforming the culture of geothermal bathing into a central aspect of national identity. Geothermal heat is also used in various industrial processes, such as number 1, drying seaweed and fish for export. 2, production of sea salt through geothermal evaporation. 3, dehydration of concrete to accelerate the curing process. And number 4, extraction of silica and other minerals from geothermal fluids. However, despite all the benefits, Icelandic geothermal energy faces challenges. Number 1, geothermal fluids contain corrosive minerals and gases that can damage equipment, requiring special materials and frequent maintenance. 2, deep drilling is expensive and not always successful, with costs reaching $5 million per well and significant failure rates. To mitigate these problems, Iceland continuously invests in research and development, including improved drilling technologies and gas filtration systems. Countries such as Kenya, Philippines, and New Zealand are already following in Iceland's footsteps, with geothermal energy representing significant percentages of their energy matrices. Kenya, for example, already generates more than 40% of its electricity from geothermal sources. Turkey has emerged as one of the fastest-growing geothermal markets, quadrupling its installed capacity in the last decade. In Indonesia, with the largest geothermal potential in the world, estimated at 29 gigawatts, dozens of projects are under development to harness this abundant resource. These lessons are particularly relevant for countries seeking to decarbonize their heating systems, which represent a significant portion of global greenhouse gas emissions and are often neglected in discussions about energy transition. The story of geothermal energy in Iceland is a notable example of how a country can transform its natural characteristics into technological and economic advantages. In an era of growing concern about climate change and the need for decarbonization, the Icelandic model offers valuable lessons on how to develop sustainable and integrated energy systems. While other renewable sources, such as solar and wind, receive more media attention, geothermal energy remains a fundamental resource for a clean energy future. Constant, reliable, and virtually inexhaustible, Iceland shows us that sometimes the solutions to our most urgent energy challenges may be right beneath our feet. And perhaps more importantly, it demonstrates how a small nation with a long-term vision can transform itself from a dependent importer of fossil fuels into a global clean energy leader in just a few decades. What did you think of this dive into the world of Icelandic geothermal energy? Leave your comment below and don't forget to subscribe to the channel for more content on technological innovations that are shaping our future. See you in the next video.